Sorry, no worries, thank you. So preventive care, we might educate our members on preventive care options that they have that are covered by their plan. Of course, the play here is that if a member stays on top of their preventive care, if they go to their annual doctor's office visits, for example, they're going to have better long-term health and have less medical expenses. Similar idea for the second bucket here, medication adherence for our members that take prescription drugs to manage chronic conditions. We can, of course, encourage them to stay on top of these, but we can go farther. We can let them know when their prescription is running low. We can even make recommendations and say, hey, there's a generic version of a drug that you're taking. And if you switch to the generic version, it does the same thing medically, but you will save money out of your own pocket. The third bucket here, preferred site of care. I can motivate with an example. Let's say a member needs an x-ray. They might say, you know what, I bet the nearest hospital has an x-ray machine. I'll just go there. That's technically true. Any hospital will have this, but it's probably going to be super expensive because everything is more expensive at a hospital, and it quite possibly could be out of network. So we might predict what member is going to need an x-ray, send them some messaging saying, hey, if you happen to need this service, here are a couple of in-network low-cost clinics near you. Again, same idea. If the member saves money out of their own pocket by getting a cheaper version of an x-ray, we will save money on our medical claim spending. So before I go any farther, a couple of different ways we could run these campaigns. Obviously, what we don't want to do is message every member with every bit of messaging. That would be way too much. It would be a bunch of not relevant things for members, and no one wants a bunch of unnecessary communication from their health insurance company. And so generally speaking, what we want to do is tailor this communication in some way. So obviously, predictive modeling is a good use case for this. I want to talk about the data that we might use to do this. So as a health insurance company, of course, our major data form is a medical claim. When a member goes to a doctor's office or the ER or the hospital, we will get a medical claim talking about that medical experience. So specifically, the most important data that we get from these claims is medical codes. I'm going to talk about three types: diagnosis, procedure, and prescription codes. So if I go to the doctor, depending on what's wrong with me, there will be one or more diagnosis codes on the claim. If I get a surgery done, there will be one or more procedure codes on the claim representing the work that was done. And if the doctor prescribes me medicine, there will be prescription codes on the claim that show the medicine I was prescribed. So these are the most important forms of data that are on our claims. So to bring this to life a bit, on the right hand of the slide, I've included some example diagnosis codes. So I want to draw your attention to a few of them. This third one down, T33, this is superficial frostbite of the left ear subsequent encounter. These codes can get very specific. There is a different code for superficial frostbite of the right ear subsequent encounter, and there are different codes for superficial frostbite of the left ear first encounter and third plus encounter. So these get very, very specific. They're also pretty broad. You can see this one second from the bottom, struck by parrot subsequent encounter. My working assumption is that if there's an ICD code for it or a diagnosis code, someone at some time was actually diagnosed for it. And so what this means is that someone somewhere was struck by a parrot badly enough multiple times to need medical attention and get diagnosed with this stuff. And finally, you can see the last one, problems in relationships with in-laws. Just to show like how broad these get, they seem a little wacky, but this is apparently something that you can get diagnosed by your doctor. So this is the type of data that we use. These are the diagnosis codes only. Again, there are also procedure and prescription codes for diagnosis codes that are over 10,000 individual of these codes. So now I want to talk a little bit about what are embeddings, why we might use them. It's going to keep this pretty high level. At their simplest form, embeddings are a numeric representation of complex data. So the first example here, you can take a word like the, THE, put it through an embedding algorithm. You will get out a list of numbers or a numeric vector. The length of the vector is basically a hyperparameter that you can play around with. You don't have to stop at words, though. You can do this with a sentence. You can do this with an entire book, any sort of document you can embed into a numeric vector. You don't even have to stop at text, though. You can do this with any data, including images. So what do we get out of this? Why would we want to do it? Now, if I give you a couple words like dog and cat and rock, we know as English speakers that dog and cat are probably more similar than dog and rock. Dog and cat are, of course, both animals, both mammals, both have 4 legs. But this is subjective. This is just sort of based on our domain knowledge. We can't say this in any quantitative way. Now, if we embed these words into a numeric vector, this opens up a whole world of possibilities of comparing these things quantitatively. We can come up with some sort of distance metric, and if the embeddings are well trained, we can say quantitatively, numerically, certain words are more similar to each other than they are to other words. And we can extend this concept again, sentences, images, any other type of data. Once we have them in embedding form, which is to say numeric vector form, we can do all sorts of comparisons or predictive modeling or clustering. So embeddings at their core are unsupervised learning. If I give you the embedding for a word, there's no way to say whether it's right or wrong. It's just a subjective form of learning. One of the ways that we can start evaluating them, though, to take the natural language use case, is to see if they capture relationships that we know are true based on our common sense or based on our domain knowledge. So looking at the example towards the center of the slide here, we take the abstract idea of a king, subtract the notion of a man from that. It should be pretty similar to taking the idea of a queen and subtracting the idea of a woman from that. Now, again, this is subjective. This is based on our understanding of language. But if we take the embeddings for these words, we can actually just run this exact calculation and see if it's true or if it's nearly true. So this would just be a one-off spot check sort of example. But for the natural language example, you can take something like this and see, are these embeddings actually capturing the relationships that we know to be true based on our domain knowledge? In a couple of slides, I'll talk a lot more about evaluating these embeddings, so more to come on that. So now let me talk about how we specifically use embeddings. So I mentioned before that we run these member marketing campaigns or these member behavior change campaigns. We want to use the medical codes contained in our medical claims to build predictive models to identify the members that are best suited to receive this messaging. As I also said before, just for our diagnosis codes, there are over 10,000 of these. They're just alphanumeric strings. So how can we use them? One way to do it might be one-hot encoding, but since there are so many of these codes, what we're going to end up with is a very, very sparse vector. Specifically, it's going to have about 9.9 thousand zeros and one single one for the relevant diagnosis code. So that's probably not the best way to do it. As you've probably guessed from the title of this talk, embeddings are how we elected to pursue this. So what we're going to do for each of these codes, we're going to train the embedding, we're going to get a numeric vector out, and then there's a bunch of different things that we can do downstream with that I'll talk about. In the interest of time, I'm going to move through this slide. So this slide essentially talks about what we do in this project. We take our members' de-identified medical history. So these are these medical codes, diagnosis, procedure, and prescription. I have a fictionalized history here towards the center of the slide. So this particular member had claims on January 1st, February 1st, and March 1st. You can see the diagnosis codes here. So in the natural language example, we would feed sentences usually into an embedding algorithm. So we would feed the cat chased the dog, the parrot hit the human, whatever the sentence is. This is what goes into our embedding algorithm. In our case, our sentences are going to be these sequences of codes for a given member over a given period of time. These are obviously much less intuitive. We as humans can't just read the codes, but from the point of view of an embedding algorithm, it doesn't really matter. Each of these codes is still a token, just like a word would be, and this is how we do our training. So training these embeddings, it's an active field of research. There's a bunch of different ways to do it. It's a bit outside the scope of this talk, so I'm going to abstract away from it. We can talk about it more if there are questions and if we have time. But basically what we're going to get out of this, for each diagnosis, procedure, and prescription code, we're going to get a numeric vector representing that code, obviously in numeric form. So once we have this, we can essentially take a simple average or a weighted average at the member level, and what we'll come out with is for each member a vector that represents their average diagnosis code, their average procedure code, or their average prescription code. So now we've taken these medical codes that represent a member's medical history, we put them in numeric form, and we've condensed them down to be at the member level. So we have this sort of member level representation of that member's medical history. So now let me talk about how we evaluate these. So I mentioned before that embeddings fundamentally are unsupervised learning, so there's no right or wrong answer. The first approach we generally took was sort of a descriptive analysis approach. Do these embeddings seem to capture logical relationships that we know are true from domain knowledge? So here's what we did on this plot. This is after the embeddings are trained for diagnosis codes specifically. We dimension reduce them down to 2 dimensions, essentially crunch them down so you can plot them nice and neatly. What we also did was we color coded them by diagnosis group. So diagnosis group is a higher level grouping. For example, you might expect if there are 100 individual diagnosis codes that relate to eye disorders or diseases, they would all roll up to one single diagnosis group that relates to eye disorders or diseases. So that's where the color coding comes from. And then of course, we've also overlaid some of the names of these diagnosis groups. So a couple of things jump out from this plot. First of all, we can see that a lot of these colors are clustered together by color. So that's a good sign. I'd say subjectively, we would expect that eye disorders would all show up together on this plot. If everything was completely scattered everywhere, we might get a little worried that these embeddings aren't actually capturing anything useful. I want to talk about a couple of these more specifically though. We can see towards the left-hand side of the plot, this green cluster that relates to pregnancy. You can see that it's sort of set off from the rest of the points. From our domain knowledge, this actually makes a lot of sense. Pregnancy is the only thing that we deal with that is not a disease or a disorder. Obviously, it's something that people generally want and plan for. And so it makes a lot of sense that these diagnosis code points are separated from the rest. If we look below and to the right of this pregnancy cluster, we can also see other diagnosis groups that are primarily or exclusively related to women. And so again, subjectively, what we're seeing is that these embeddings seem to be capturing semantic relationships that we would expect to see based on our domain knowledge. So the rest of this plot is a little bit hard to interpret without more specific medical knowledge. So I'll leave this one here, but so far so good. We're seeing subjective relationships that we would expect to see. Now, continuing with this line of reasoning, I'm going to start with the center plot here. What we're looking at here, instead of diagnosis codes, we're looking at procedure codes. And instead of individual procedure codes, we have averaged these at the member level. So we basically took for each member their procedure codes in some time period, took a big average of that. And so each of these points represents a member. Now, looking at the middle plot, we can see that these are split out by male and female. And what this plot tells us is that we can see some regions that are mostly blue. This means that these are procedures that relate mostly to women. And we can see a bunch of areas that are mixed. Blue and yellow. So this means these are procedures that relate to both men and women. Now with this green rectangle specifically, what we see is a pretty big cluster of points that are separate from the rest of points. As we saw with diagnosis codes, when we zoomed in on this, we found out that these were members on maternity or pregnancy journeys. Same sort of reasoning applies here. Pregnancy procedures are the only procedures that we deal with that are not for some sort of disease and disorder. And so it makes a lot of sense that this is a big cluster, and B, separated from the rest. So looking at the plot on the right, we've done basically the same thing, but we split out by age instead of gender. You can see the age buckets on the plot. So generally speaking, what we see is that certain procedures relate to certain age groups. This is pretty intuitive. Young people, if they're getting procedures, might have completely different procedures than if someone 65 plus is getting a procedure. Zooming in again on this little pregnancy island from the center plot, we can see that that age group is 18 to 35. And so this again makes a lot of sense. If we're talking about pregnancy, 18 to 35 is a very reasonable age range that we would expect members on a pregnancy journey to be in. So overall, these last two slides are a subjective or a descriptive analysis way to look at our embeddings and see if they're capturing useful information. What we can't do with this, though, if we train 10 different versions of embeddings, if we create these plots for all of them, it's not going to let us say, well, is embedding version 1 better or worse than embedding version 3? So how did we get around this? What we started doing was taking these embeddings, again, averaging them at the member level, and then we're using these as features to predict a bunch of different medical events. You can see these on the plot. We have, for example, C-section delivery. We have physical therapy, radiology, a couple different types of emergency room visits. So the idea here is to see, can these embeddings actually predict medical events that we might be interested in? And this is just kind of a small subset of a lot of different types of events we might be interested in. So these are what the orange bars show us. You can also see the green bars on here. So these are very simple features. You can think of these as a dummy model or a baseline model, basically the most naive features we can come up with. They're basically group counts for diagnosis codes and procedure codes. So not only do we want to look at, can these embeddings predict anything, we want to see how they perform against very, very simple features. At the end of the day, if they can't perform baseline features, then there's really no point of using this stuff, at least for predictive modeling. So luckily, as you can see, the orange bars are typically bigger than the green bars. So thank goodness this whole project wasn't just a big waste of time. But that's not always the case. You can see in the second category down for nephrologist visits, for whatever reason, the embeddings don't perform as well as the group counts, but overall embeddings outperform group counts. There are also a couple other interesting things on this plot. So these categories are roughly ordered by ease of prediction. So what you see at the top, C-section delivery, this is the most predictable event on this list. This makes a lot of sense. By the time a member is having a C-section delivery, we almost certainly have other claims, maybe ultrasounds, maybe other doctor's office visits. And so we would expect C-section delivery to be a fairly easy thing to predict compared to the other things we're interested in. If we look at the bottom though, these last four categories are all different types of emergency room visits. These are obviously the hardest things to predict. Again, this is pretty intuitive. If someone has something unexpected happen, some sort of car accident or burn or trauma, the ER is probably where you'll end up. And so it makes sense that we would not be able to predict ER visits based on your past medical history, because in many cases, going to the ER is completely independent of your previous medical history. So overall, this is the subjective, or excuse me, the more objective or the more quantitative way that we use to evaluate these embeddings. And we don't have it on the slide here, but with this method, what we can do is compare different versions of embeddings and say, okay, embedding version 1 is better or worse than embedding version 3 based on its average performance on all of these different types of predictive tasks. So I want to talk about today how our team uses these embeddings. Two main ways. The first is that these embeddings basically serve as free features. So if you have a model that's running, you can quickly compute these embeddings, plug them into your model, see if they improve the performance. We have a couple examples of this. In one case, with other changes, embeddings added about 40% to the recall. So that's been our one big value lever there. The second big bucket here is if a data scientist is working on something new, a new idea, a new project, and they need a model, instead of spending days or even weeks on a lot of custom feature engineering, at least for a V0 model, they can quickly pull these embedding features and just understand roughly what their predictive power is and get to a go, no-go decision more quickly. So these are the two main ways that our team is using the embeddings today. Finally, some next steps. So these are implemented through a Python package, which is great because anyone who wants to use them doesn't always need to come to our team to learn how to use them. What's not great about that is we don't actually know everyone who's using them. I'd say about once a month, someone pings me about this and I'm like, I had no idea you were using this, but that's great that you are. So we're working on ways to actually track who's using this and eventually get at an idea of what the value of it is. Point number two, as you might expect, we're always testing new embedding algorithms. We've tested things like word2vec, BLUB. We've also tested more advanced transformer-based architectures like BERT. Point number three, exploring embeddings for other types of codes. I've talked about diagnosis, procedure, and prescription. There are also lab codes. We could also think about embeddings, trying to train them directly for members or doctors or even facilities like hospitals. So a lot of different things we could think about there. And then the fourth point here, I've talked mostly about using these embeddings in the context of predictive modeling. We can do other things with this. We can obviously do similarity measures. We could compare members or doctors or facilities. We can also do different types of clustering. So a lot of other downstream applications besides just predictive modeling. So that's everything I had prepared. Last thing I will say, so as I mentioned, Aetna is a CVS Health company. CVS Health is hiring aggressively, have been hiring aggressively for the past few years. If this work sounds interesting, if helping people on their healthcare journey sounds interesting, I recommend you go to cvshealth.com and check out our careers page. Otherwise, happy to take any questions at this point.
Have you explored using embeddings for risk stratification?
For like risk scores? Yeah, it's on a roadmap. Haven't had a chance, but I think it's a really logical application.
Yeah, you mentioned that this is in Python. Do you have like a system that you're then like running those in across, or just either like randomly running it on their machines and stuff? you have like tools and like that you're using on top of that? Okay.
Yeah, so it's a Python package, but fundamentally what it does is it's basically a join. Like you have your codes and they join onto the table. The embeddings that we've implemented are static. It plugs into other tools that we have to help someone scale if they're running this on 50 million members. We have other tools for that. But since those tools already existed, we just had to kind of worry about this small part of the universe. We don't right now. Physician free text, we think is really valuable. It's a little bit hit or miss in the sense it's not on all of the claims. And so what we liked about this first approach is that medical codes are on all the claims. But obviously, I think there's a lot of stuff in doctor's notes that you can't really get from just looking at the tabular data in a claim. So the closest thing we use is basically this predictive performance. This isn't exactly evaluating the embeddings. It's more saying if the embeddings can predict medical events really well, that's mostly what we're interested in. And so we will consider those to be well-trained embeddings.
My question is actually about this slide. How far out did you stop taking data time-wise before evaluating the NUC on this?
I think these were done on 90 days out. I mean, for certain events, like that time frame might not make sense, but I think the point would be as long as all of the embeddings are still trying to do it, they would all kind of have the same bias or the same challenge.
Just for like C-section, like if you take data up until like 2 days early, you see like a eclampsia, and that's going to boost your NUC.
Sure. Yeah, it's a really good question. We kind of have to balance. So yeah, for example, embedding version 1 might be really good on certain types of events, but embedding version 2, while worse overall, is better on other types of events. We have to basically balance that between when promoting this to the larger team, are people really going to like comprehensively read documentation on 10 different sets of embeddings? So the approach we're taking right now is kind of pushing out the best overall version. But I think in the future, especially for really well built out projects, we could go to them and kind of say, hey, there are different versions of this, and it might be worth your while to find the embeddings that work best for your specific use case. Portion of the just our overall data. We had to go through a legal review, so I think I probably can't say anything more than that. We haven't specifically looked at that, but I would safely say there definitely are. Definitely data scientists. The primary use today is if you have a predictive model, throw these embeddings in there as features, either additional features, or if you don't feel like building your own features, just use these. Cool. Any other questions? We used UMAP specifically on this one. I don't remember the library, but I would hope in theory, even if you use like PCA, you would see pretty similar results, would be my assumption.
So I want only if lots of features, I guess each of the stuff present one person at one subscribe.
So each of these actually represents a diagnosis code.
So I was wondering, if you do the CCA with features, and then after the CCA, just have the personal of the CCA. Then keep the same color code, the same, but just show this scatter on the personal of the CCA. Then it might be quite nice because pregnancy cluster is the less severe disease that is close to the scope. So then the pregnancy might go to like the right or end of the first month, and then once the disease becomes severe, then to have a nice separated clusters of the disease that are scattered along the first month of the CCA. It might be worse than explore. So
Yeah, makes sense. That sounds reasonable. We have a lot of, I don't think we've done that specifically. We do have a lot of descriptive analysis, and these were kind of like the most compelling ones that I found.
Any other questions? Well, with that, can we thank our speaker, Dave Bansal?
Thanks, everyone.
Please enjoy the rest of DataCon LA.